everybody. Welcome to the second day. And I think the day will be devoted mostly to the switch. We start with Giulio.
Thank you, Czaslaw. Well, it may sound unusual, but I would like to start by thanking the organizers. I mean, not myself and Marius, but Destiny and Maria, who are really the people who allowed us to keep our sanity in this weird organization of the workshop. So a big thanks to them. And Maria is our local contact person that helps and has done way above and beyond what should be her job. Okay, so today I give a sort of introductory talk. I thought that since this is a kind of a broad meeting, it would be good to first give basic definitions of what the quantum switch is, and then to quickly review what has happened since the time we introduced until now. There has been a pretty rich story, and even if I had a full hour, I wouldn't be able to cover all the details. So apology for those who have worked on this and will not be mentioned in my talk. This is not meant to be the review of everything that has been done, but it's a bit of a story that I found interesting, and of course is biased and related to my own work mostly. So the quantum switch, I mean, had itself a pretty weird story. I mean, this was a paper we submitted in December 2009 with a lot of excitement. We wrote this abstract that sounds almost funny and cute and naive seen now. I mean, there are very things that we are very excited about. Say, this is really, this indefinite causal order is a new way to think about quantum computation. It will have a huge impact on quantum computers. We have this new idea of quantum circuit with the geometry of the connection in a superposition. It is an unexplored aspect of quantum mechanics in non-fixed causal background, and it goes far beyond computer science. Good that we said that at least, and maybe of relevance to quantum gravity. I mean, this paper, of course, was rejected a bunch of times by all the high-impact journals, and eventually got published 4 years later in PRA with a much, how can I say, much modest abstract. And what I feel by looking back at these 10 years is that the truth is somewhere in between. So this was really kind of getting on the kind of self-limiting view on what we have done, and this was kind of dreaming of what could have happened. And a lot of things that are in between this and this did happen, and this is what really my talk is about. It's about what did happen, and why somehow some of these slightly naive statements have been vindicated by time, in a sense. So the outline is this. I will start from the old stuff, from the basic definition for why the switch is incompatible with definite causal order, and then we talk about some of the first advantages that have been discovered, like why this is interesting for quantum information. So a semi-new thing is that in the meantime there have been experimental implementations with quantum optics, and there is a debate about which implementation and which physics would really count for a realization of the quantum switch. So this is kind of more recent stuff. People are still discussing about this. And I will conclude with the two new sort of perspectives. One is about the application of the quantum switch to the theory of communication, to Shannon's theory of communication. And the last one is a very new work on precision measurements and quantum metrology. So let me see if I can get through all these things. I will say I will probably take some of the question time for the actual talk. The reason why I feel confident doing that is that today is a very consistent day in which we will talk about different aspects of the quantum switch. So it's not that this is the only chance to talk about these things and to discuss. Okay, so let's start from the basic definition, and since we are from slightly different communities, let me give you some very basic preliminaries. What is a quantum channel? So in quantum information we call quantum channel the most general evolution of a quantum system. I will use a lot of these graphical pictures to make things prettier. So there will be a box with an input pipe and an output pipe. So here the input states come in, and here the output states come out. So this is the most general evolution you can imagine for the density matrix of a system. Whatever takes density matrices into density matrices, even when you apply locally on a composite system, has the right to be called a quantum channel or a quantum process. Mathematically, the way you represent this, the most convenient way, one convenient way, I would say, is the Krauss representation, is this sum. You multiply the density matrix by some operator and its dagger. The simplest case, of course, of this is the unitary evolution of the density matrix when you have only one term in the sum. This is u rho u dagger. This is the adjoint action of the unitary operator u on the density matrix. So this is kind of a generalization of the unitary evolution to the most general processes you can have in quantum mechanics. typically noisy processes when you have more than one term in this sum. All right, these are quantum channels. One thing that we do a lot in quantum information, quantum gravity-inspired approach is to connect processes together. So we build the circuits by connecting channels together. And here I highlighted the connections in blue. So this operation of connecting things is an operation we do on the channels. So the channel transforms density matrices into density matrices. The operation of sticking channels together transforms channels into channels. So the connection is a map that transforms some input channels, like A, B, and C in this picture, into a bigger channel that is the one that comes by linking them together. So this idea is strongly related with ideas that Lucien Hardy proposed even outside quantum mechanics in 2005 with the causal framework, and we will have at least one talk on this tomorrow.
Specific technical questions or not even those?
Please, yes. Anything that has to do with understanding what I'm saying, yes.
Crucial for my
Yes.
Input and output, or just...
In my picture, the inputs are on the left and the outputs are on the right.
No, but what's the difference between the input and output? Is there some equation that distinguishes paths?
It's mostly grammatical. Yes, good question. So this is mostly, sorry, time is going the other way around here, no? It's mostly a grammatical difference. So the input, well, not just a grammatical difference. So there is this normalization of condition of the channel. This tells you that this is basically the fact that if you trace the output, so the trace of the density matrix is 1 independently of which density matrix you put. So this condition is asymmetric.
So it's not true that sum over E of Ci star is identity?
No, that's true only for a very, very special type of channels called unital channels or bistochastic channels. Of course, that was a good point. So here there are two equations. So unitary evolution is time symmetric for what concerns the grammar of writing down things. A general channel is not.
You assume breaks time reversal invariance. You make this assumption that this is...
As I said, this is just a characterization of this sentence. So really what breaks time invariance is the convex set, the structure of the convex set of density matrices. Already everything is written. When we say that the quantum states are trace 1 positive matrices, we are already yelling causality in the strongest possible way, because the most general map that maps a density matrix into a density matrix in a reasonable way must satisfy this condition. So, I mean, it's a deep point, and I'm very happy to discuss. Unfortunately, it's not quite, I mean, there are so many things to say. So, but basically, causality, this asymmetry is already encoded in the set of density, in the geometry of the state space of density matrices. Not of pure states in general, but of density matrices. If you take this convex set, this is just a characterization of the most general transformation of density matrices to density matrix. It did happen. I knew that. Yeah. All right.
Maybe like this.
How about putting it?
Sorry? So channels
Yeah.
are, or just the equations are not, right?
How can
Sorry?
the most general transformation be not inverted?
Please don't get me stuck on this, because this is not really going to. But a quick answer. So the way, if you want to realize them physically, what we know about physical realization of quantum channels is to couple the system with an environment. So the unitary that couples system and environment is invertible, but you are preparing a state of, is this the thing you said yesterday, actually? You're preparing the environment and the system in the product state at the beginning, and this is a condition that is asymmetric. Then the unitary entangles them, and you are tracing out the environment in the end. So from our perspective, if you think of the physical realization of this, irreversibility comes from this way, that at the beginning there is a product state. But the point I was making is that at the fundamental level, all this stuff is already contained into the structure of density matrices. You may not even need to talk about this physical realization. You just ask, what is the most general evolution of density matrices by some mathematical notion, and you just come out with this. So even if the word, even if Hamiltonians did not exist, at the logical level, this is the most general evolution of density matrices. All right. So I mean, yeah, I was saying, like, let's try to go faster. But in fact, I think it's a good point if we manage to clear these points among us. Yeah, that's, I think, is part of the point. So yes, sorry, I should be more relaxed, because it may be more important to clarify these points than actually getting through the whole stories of what happened to the quantum switch. So yes, all right. So yes, this way of transforming channels into channels, among other things, can describe the operation of connecting them together. No? So you have a bunch of channels in the input and some abstract operation that connects them, and this could describe the structure of space-time. Like space-time decides what is close to what, and which inputs are connected to which outputs, because they are kind of local, they're touching each other in space or in any other way. So, yeah. So the quantum switch is a special type of connecting channels, is a special supermap, and so the simplified version of the quantum switch is the following. There is a supermap, is a high-level map that takes two channels, takes two physical processes with equal inputs and outputs, and connects them in a quantum superposition of two alternative configurations. So you have channel A and channel B, and you either stick A before B, or you stick B before A. Notice that I'm still putting this blue line to represent what we are, the operation of connecting. So this is what we do, or what space-time does. It connects A and B by linking this output to this input in two alternative ways. So this is the simplified switch, where we do connect things. And this has been used a lot in the literature afterwards. So when people talk about the quantum switch, they normally refer to this. So mathematically, you can write your input channels in the form that I showed to you before. It's a sum of operators with this operator and its dagger. You can do this for channel A, for channel B. And the quantum switch is a third channel that you can synthesize by combining A and B. That has this form, again, is the form of a quantum channel, where now the operators are kind of controlled combination of A before B or B before A, controlled by the state of a qubit. So there is a quantum bit, a two-level system, that decides whether you put A before B or B before A. And you can think, I mean, this is purely abstract. If you think in kind of the gravity framework, this qubit could be some coarse-grained description of the structure of space-time that decides what is before what. If you do it in a quantum optics experiment, you can set up, for example, the polarization to control the path. So these things may not be directly space-time as such. So this is a very abstract way of realizing things. So here you are connecting you are multiplying the operators because you are connecting them together.
And so you add also this degree of freedom into a density matrix?
Yes. Yes. So the new channel that I build by combining A and B has one extra input that is the control. Or if I think in a space-time picture, I can think that this control is fixed by nature. I mean, there is some state of the background, and then I get a new channel with a new output, this degree of freedom that I could potentially observe in the output.
And this was not already one of the possible transformation of the set of three things, the two possible channels and the control bit. I mean, was not already available as one of the possibilities in the...
It was not presented before. I mean, it is allowed by quantum mechanics. That's how we define. It's one of the high-level operations that quantum mechanics or quantum probability theory allows us. So it's one of the logically conceivable ways to combine channels.
I mean, if as input you have the input you have and the qubit, and as output you have whatever. So,
yes.
Is it just one of the available possibility already without building it explicitly? Wasn't that included?
So this thing is a quantum channel. This thing is a quantum channel. So it is a possible transformation in quantum mechanics.
So you're not adding something, it's just something that was already there.
So this box is something that exists in quantum mechanics and can be realized in the way we said before. The switch is the transformation from two input boxes to this one. So somehow is the operation of time delocalizing things to respect to each other. So you give me two boxes, interaction A and interaction B with their own environments, and I have the power to stick them together and produce this one. So A and B are things allowed by quantum mechanics. This channel is a channel allowed by quantum mechanics. The operation of building this from A and B is what we define. The quantum switch is the operation that builds this from these two ingredients. So we are replicating this idea of defining axiomatically things that transform other things that we know. So density matrices into density matrices, like forget about all the physics, like see what is logically possible. And now let's transform channels into channels. So forget about the physics. Let's see what is logically possible without killing probability theory.
But the physics also makes it possible. Why shouldn't the physics?
Well, that's one of the debated questions, like which physics
Maybe
makes
the
it.
reason we haven't seen this before is that if you look at the definition of the quantum circuit, it's really very restricted, and it's basically the quantum channel, not a control of quantum channel. If you strictly stick to pictures of the quantum circuit, of the computation, of course it's allowed for physics, but people didn't think maybe about it because of...
Well, there is, I would like to make a point about this thing of the super maps, this abstract approach. So as you know, we don't have a full picture of what quantum gravity is. Presumably,
Quantum gravity is standard quantum mechanics.
sure, no, but what I'm saying is that we don't have a picture of quantum gravity is. So there is some physics that we don't know, and probably that physics will include, at the local level, quantum mechanics in the way we already know it. So supermaps are a way to guess what would be possible in a more general theory that is compatible with what we have already. So this abstract way is a way to say, I can say that
Something that
logically,
is not already included in standard quantum mechanics, or just...
this map per se is not clearly included in standard quantum mechanics. Well, let me give the talk. That's one of the things. No, I'm arguing that first of all, there is this abstract approach that already delivers results, and the talk is about those results. And there will be some discussion of the physical implementations of this. But this I'm inverting the approach. I'm not taking some known physics and then say, we can build this. I say, what we can conceivably build without having logical contradictions? It's a bit like closed time-like curves, no? Some equations allow you closed time-like curves. The world in which we live may not have them. So one thing is the statement of what we can do in this world, and one thing is what is logically possible.
Okay,
Yeah.
I understand. But this thing that you're defining, forget whether it's logically
Yeah.
possible, can be done in this world. I don't see any reason why it shouldn't, from your definition here.
This can be done.
Why is not a channel?
Well, but let's go on and talk a little bit about things that that can be done here, because there is a sense in which this cannot be done, and there is a sense in which it can. So it's all about looking at the details and looking at these things. So I cannot just say it can be done. Yes, no, it depends on what we mean by realizing. What does it mean to realize a function of x, to realize f of x equal to y? What does it mean? There are models of computation that tell us what that means. There are other ways in which you could say, okay, there is a function, two things depend on each other in a certain way. One thing may be a computation, another may not. So there is more of a subtle and nuanced question than something that I can answer on the spot like that.
Oh, can I add something very briefly?
Yeah.
So just say, basically restate what Giulio said, but can be done, can be realized, it's really not clear, right? So you need to add something more, can be realized with quantum circuits, can be realized deterministic,
That's the question I'm asking, is not at all.
Okay.
So maybe
Maybe we should.
Okay.
That,
I think we should.
not asking a question concretely. You gave a definition for channel
Yeah.
to start with. Is
Yes.
that one of, does it belong to the channels to start with?
So, but first of all, let me say that quantum mechanics doesn't talk whatsoever about this higher order transformation. So quantum mechanics tells you about the dynamic of
The
systems.
definition of a channel is a match from density matrices to density matrices.
Is that
The
one of
switch-
those?
What is the bottom is yes, but the switch itself is not a channel. It's a map from channels to channels.
I
So it's a pi-
understand.
yeah.
But imagine
could be
channel,
good at a
a channel into some other channel. This other channel is just one of the channels I
Yes.
started from.
Yes.
Yes.
So if
the
you want, you
individual-
can just build this channel.
Yes.
But building this channel doesn't mean implementing the transformation from these two input channels to it. It's a different thing, no?
Okay, but
So, for example, you can always make a sandwich from some whatever, from some bread that has already been cut and from some ham that has already been cut. And one thing is to build the sandwich from, I don't know, from wheat and whatever sort of animal we went inside the sandwich. So one thing is the process of building something, and one thing is just that thing. So,
okay,
so
but
yeah.
excuse me. So to go past this, if we fix A and B, the channels, S of A and B for A B fixed
Yeah.
is a channel.
This
That's
is a
what
channel.
tells us.
Okay, but the answer to that is trivially yes.
Yes.
That's how the switch is defined. It should map channels into channels, and all channels are in principle allowed by quantum mechanics as we know. Like the mechanics of the systems we know allows quantum channels. But the switch is not this channel. The switch is the transformation from these two channels to this one. And quantum mechanics doesn't say anything about this. So at least quantum probability theory, or what is the logically conceivable thing, allows us to talk about these things. But quantum mechanics is silent on whether these things can be realized or not. It's not even clear what it means to realize a transformation of processes as opposed to transforming states. Quantum mechanics is all about transforming states. It tells you, if you know the Hamiltonian, what is the unitary evolution. It doesn't tell you anything about how you transform processes. There are some heuristics, but it doesn't definitely talk about these things. All right. So more generally, what is really the quantum switch is a situation where instead of connecting these two boxes, these two channels together, we leave a hole in between, so that we leave the space for some intermediate intervention that somebody may want to stick in. So it's sometimes useful to consider networks with open slots, like here. And the quantum switch is the open slot, the full quantum switch is the open slot version of this. So is a supermap that takes as input two processes, A and B, and produces as an output the superposition of the two processes placed in one order or in the other without the connection in between. So it's minor difference. So again, now I think I understand the point of our discussion before. So really the switch is the process that goes from here to there. What is here is already in quantum mechanics. What is there exists in quantum mechanics. But whether you can do this mapping is not clear at all from the rules of quantum mechanics. So that's the kind of new dimension that our work added. We consider these higher order maps. Right. So that's the full quantum switch. And this is important because the fact that we don't connect here is conceptually important, at least. Not so important for the applications. But if you have the full quantum switch where you don't connect, you become able to generate all sorts of permutations. You have more than two channels. So it's kind of the generator of all sorts of superposition of orders that you can build. And you can also stick stuff in between. So it generates a whole family of circuits. And I think in the next talk we'll have more discussion about all circuits that you can build with superposition of processes. So it's kind of, and it's going to be even more general than just what you can do with the switch, I think. All right. Sorry, let me try to gauge myself. So how?
You said on 5 past will be 30 minutes, and now you have 7 minutes to 5 past. All right.
So mathematical definition of the full quantum switch is like the one you saw before, where instead of multiplying these operators, you just tensor them. Tensor them means that you put one operator on the degrees of freedom of the system that comes first, one operator on the degree of freedom of the system that comes later, and you don't contract them together because there is space to put something in between them. So basically these matrices act on systems that act in different time slots. So this is the full quantum switch, mathematical definition. So when we talk about the quantum switch, we talk about the map that goes from A and B, you can imagine like two boxes here in the lab, to a new box that has these operators. All right, so let's now start talking a little bit more about realization of things that would look more like a realization. So first of all is like the way you cannot realize the quantum switch. So this is a theorem that was in the original paper that says that it is impossible to find 3 quantum channels with arbitrary inputs, outputs, whatever you like. So you cannot find the 3 quantum channels C1, C2, and C3 with the property that you obtain the quantum switch, so the channel that we were talking before, the channel that exists in quantum mechanics. So you cannot produce this channel by just sticking A and B inside the quantum circuit. So you cannot make this circuit where at every time step there is something happening. So you do first your operation, then you apply your variable channel A, then another operation, apply the variable channel B, another operation. There is no way to reproduce the quantum channel S of AB in this way. So this is something that already now we are talking realizations, or we are talking no realization. We are saying that this is not a realization. You cannot do it in this way. So there is no way to do it, even if you restrict yourself to unitary channels A and B. Even if you just care about unitary processes, there is no way to generate the same channel that you have in the quantum switch from 2 unitary processes by just sticking them in a circuit with a well-defined order, where let's say process A is before process B. So we prove this impossibility result. This is not even a quantum result. This applies even to the classical switch where you just choose between two alternative orders, A before B or B before A, without superposition. So the same theorem holds if you exchange the order and even if you randomize the order. So basically the take-home message is that producing the quantum switch, so operating the quantum switch, cannot be done in this way. It cannot be done in the standard framework of quantum circuits. You cannot just, in the standard framework of quantum circuits, after you place a channel in a certain point, it's kind of rigidly fixed there. You cannot exchange the order anymore. So this is an impossibility theorem. Let me give you a bit of intuition for why this is impossible. This brings us to some other type of realization. So there is a sort of relation between being able to realize the switch in a circuit with definite time steps and having time loops. So the way that we proved the previous theorem, so the impossibility result that I showed before, that the switch cannot be realized in a fixed causal order, was to prove that if you could do that, you would have a deterministic time loop. You would have a way to send the quantum states deterministically from the future to the past. And this would violate the rules of probability theory, of quantum probability theory. You would be able, in this case, to get probabilities larger than 1. That's the logical contradiction we get. So there was a sense in which the switch was connected with the loops, and we also showed that the converse is true. So if you have access to some magic physics that gives you a deterministic way to send quantum states back from the future to the past, then you can build the quantum switch with a quantum circuit with the definite time steps, where you place the input channels in steps of this circuit, and this is the circuit. So this is the circuit. Let me show. So I am getting to it. So the circuit contains a control swap operation. So if this qubit is the state ket 0, you don't do anything. If it is the state ket 1, you swap these two qubits together. Here there are the two channels A and B in parallel. Then you get a swap that does the swap only if the qubits are in the state 0 and doesn't do it if they're in the state 1. And here is the magical time loop that brings back the density matrix here back in time. So there is a way to make sense of these pictures using the language of categorical quantum mechanics and of teleportation. You can think of this as kind of exotic physics that you could have maybe in some quantum gravity scenario. Or you could think of even of this as ordinary physics, where you simulate this with a probabilistic teleportation. So you can think of this as a preparation of an entangled state, this as a Bell measurement, and there is one specific outcome of the Bell measurement that is lucky enough that allows you to simulate this time loop. So in principle, one can do experiments even on this circuit, even if it sounds crazy, because we can simulate probabilistically these time loops. We cannot really access to deterministic ones, but probabilistically we can reproduce these. Yes, thank you.
Can you go back the previous slide? Yes, this one. So when you write the converse, I understand. You also explain
Yes.
It's very clear. So if you have this loop,
Yes.
then you can do this with determinism. But
Yeah.
the first statement, isn't it a bit weird statement? Because first you prove that you cannot do the switch with quantum circuits, and then you say if you can do it, then you do a time loop.
Well, that's this thing is the body of the proof.
But
this statement is what the proof does.
Oh.
So it says if you can do that, this circuit, if you can do it with the three maps, not necessarily channels. So that's the way the proof works. If you can do it with 3 maps, this map should be equivalent to having an identity map from here back to there, and that's not something you can get in this way. And it would give you a logical contradiction. It would give you to the contradiction that 1 is equal to the square. So that's the logic. The logic of the proof is the second statement that I wrote there.
No, I understand. I agree. I just think that the statement is a bit weird, right? Because if you already stated it's impossible, then basically you're saying if 1 is equal to 0, then you can do that.
Yes. Sorry. Originally this was called the hint of the sketch of proof, and now it became just an independent state because I didn't want to lose too much time on that. But it seems that was a lost fight anyway.
Giulio, is it also assumed implicitly that this channel always contains a particle if you look at it? Like it's not a superposition.
Yes.
So it's somehow there is also a hidden assumption which
I mean, the notion of quantum channel itself is an idealization that brings a lot of stuff in. And we should at some point talk about those things too. And maybe here we talk partly about this later this afternoon.
Yes.
Later this afternoon, not now, please. All right. So now let me use the remaining time. I will breeze through that. This is not some. This is still the old stuff. So a quantum switch can be implemented. Sorry, can give us some advantages in quantum information. The one are problems where you want to test it.
30 minutes, just 30. You said that I should tell 30 minutes.
30 minutes now, yes. So you may want to test properties of these two unknown channels that you are given. So if you have the magic ability to combine them in the quantum switch, you can discover some property, like whether the operators in them commute or anti-commute, with probability 1. So in principle, without any error. And so the work that I did in 2012 was to show that whenever you fix the order, if you assume a circuit with a fixed order, the probability of error is always strictly smaller than, probability of success is always strictly smaller than 1. So the switch allows you to solve the problem perfectly, in ideal scenario, and any circuit where you fix the order will not allow you that. Later, there has been work showing like how much is the gap between them, and I think Cyril is one of the people working on that, and there have been extension to more than 2 channels of the same idea that you can discover some property more efficiently. So you can really see that. I mean, it does make a difference to be able to generate the channel or not from the original ones, because you can discover properties that otherwise you wouldn't be able to discover. So it's really operationally meaningful. It's not just some fantasy about the order. It's really something that would have implications. So the second thing is the other remarkable thing that was found was by Chaslav is a problem of communication that you can really prove that the amount of communication you need in that problem is decreased by an exponential amount from n to log n. I will not go into the details of what the problem is. The point here again is that there is a very precise operational sense in which the switch gives you a power to do stuff you couldn't do before in the standard model of quantum circuits. All right, so a very quick word on the simulation, physical realization and simulation of the switch. There are going to be 2 talks two talks today about the physical realizations, one in quantum gravity and one in quantum optics. So I will not talk about the details of this, but again, the point I want to make is that the switch per se is just an abstract map from 2 channels to a third. It's a function of channels, and it is defined irrespectively of what is physical realization. So the way we define supermaps is never to talk about how we realize them, but to talk about what we could realize in principle without violating some basic assumptions. So there are different levels of physical implementations. So kind of the craziest and strongest implementation is the one that I showed you with the closed time loop. In that case, I would say there is, real or simulated time loop. So in that case, I think there is no doubt that we are really realizing the quantum switch. We are really taking these 2 channels, we are sticking them in a point of the circuit, at a very well-defined time step, and we are doing something around them that delocalize the 2 channels A and B in time. So there are gravitational implementations, and this is the work by Magdalena Zich and Chaslav group, where you really manage to implement a sort of, to produce the same output of the quantum switch with the superposition of masses. And the twist here is that really you can claim in a certain sense that these devices are really acting instantaneously in some like each of the devices is actually instantaneously in some reference frame. So it's a very interesting realization as well. And there are tabletop implementations that use the known physics. So you have a well-known, well-defined notion of time in the lab, and you kind of reproduce the same output of the quantum switch by using somehow a memory in time and kind of delocalizing in time your devices. And there is a whole talk about this today, so we'll talk about this later. So there is a hotly debated question is, where do you draw the line? Like, what is a genuine physical implementation and what should be called rather a simulation of the quantum switch? And it has to do with the question we were asking before. One thing is to produce the output of the quantum switch, and one thing is to produce it from the initial resource of having these 2 channels. And there is a very debated question. It's not one with a straightforward answer. So what is true is that every implementation produces this channel in the output. And however, the physical mechanism that does it is radically different in these 3 types of implementation. These are really different words, in a sense. So it's a very debated question. It's like, what mechanism counts as a real realization of the function, or which language should we use to distinguish between these 3 levels? All right. okay, I had two new directions. That was really the point where I wanted to get and get to something new. So let me give you one of them, which I think is interesting for this audience. So, and especially because it's linked to the two talks we are going to have later in the afternoon. So it's the idea of talking about quantum Shannon theory, so the theory of communication in quantum space-time. So in space-times where you have superpositions of different geometries, of different connections. So as you know, like Shannon theory, like classical Shannon theory, the one defined by Shannon in 1948, is the theory of communication on which our communication systems are based. It's a mathematical theorem of classical channels. So the thing that I defined for you at the beginning, the quantum channels, are the quantum version of what information theorists consider every day, and information engineers consider every day when it comes to designing our communication systems. So this theory was completely classical, was invented by Shannon in a completely classical framework. So the states of the messages we send are classical. The communication lines are classical. They can only send the classical states. They do not preserve coherence. And the space-time in which the whole communication protocol lives is classical itself. So you have this picture where the different blocks act in a very well-defined order with respect to each other, and everything is very classical. So quantum Shannon theory, which grew to become one of the most important and most active areas of quantum information, is the quantum version of that. Is the quantum version of Shannon's classical theory, and the quantization here is that the information carries, like the stuff that's the communicating parties send to each other, become quantum systems. So we can communicate to each other by sending photons to one another. We can send photons to one another. So in principle, we don't have to send the states that are orthogonal to each other. We can create superpositions of different classical messages, like those ones. And it has been shown that if you can do these things, there are, well, amazing capabilities that you can obtain, most importantly, quantum cryptography. And there are new laws of information that you discover. I think this started from the works of Holevo and Schumacher. So a lot of things change when you are able to send quantum systems. But still, in the standard picture, the space-time in which the communication takes place is still a classical one, and the configuration in which you combine your communication devices is still fixed. So the obvious question was to think about how would communication theory change if we were living in a space-time where there are quantum superpositions of different geometries. So imagine that there are two guys, Alice and Bob, and they're using two devices, two communication devices, C1 and C2. Now the relation between C1 and C2 is not well defined. It could be that C1 appears before C2, or it could be that C2 appears before C1. This is determined by how that space-time around Alice and Bob is kind of shaped. So how is the exchange of information affected by this? So how would it be to exchange messages in a world where space-time is a superposition? So conceptually, we can think that of the following model. We can think that there are communication devices, and a device cannot be used until it is placed somewhere in space-time. So there will be some supermap, like the switch, that describes how do you place the channels between the sender and the receiver. Normally, in standard Shannon theory, they are placed in parallel, so they are all stuck between the channel and receiver. In some network scenario, they could be put in a sequence, so one before the other, and so on. And the obvious question was, how does this change if we allow for quantum superpositions of different configurations? And in particular, how about the quantum switch, which is the superposition we are the most familiar with? So a lot of things change. So we have two models of communication, one with parallel and sequential placement only. And then there is a second model where we add the superposition of orders to kind of mimic the superposition of space-times. And of course, the change from 1 to 2 implies major changes of what we find. There are advantages we find. And this can be seen both for classical and quantum data transmission. So there are a lot of works on this, and I think today we'll hear more by other speakers. Okay? Yes. So let me finish on that. So we'll hear more about other speakers, because there is a lot of discussion that is open. So the extension of quantum Shannon theory with the quantum switch, with the superposition of orders, kind of revived the interest in more general kinds of superpositions, like superposition of communication channels that were introduced by Gizen and co-authors in 2005, independently of the quantum switch. This was kind of revived, and it will appear today. It was work done by Alastair and Cyril and their co-authors. So Alastair will give a talk. The first talk of the afternoon will be about this. Myself and Clear worked on this, and I think he will also talk about this partly this afternoon. And also Chaslav group and in particular Julia were in exploring the idea of superposition of different operations you do around the channels. And I think there will be something about that in today's talk by Julia, maybe? No, not one. Okay, so you'll hear only about the experiment. Okay, good. So this is a very much debated question. So how much of the ingredients that we have in the quantum switch are critical for disadvantages and how much are not? So there are, again, this is a very nuanced question. Some answers are here and the debate is still on. So that's where I'd like to conclude. Thank you for
We had already questions, but maybe one urgent we can take.
So I think one of the, I guess, reasons for in the standard circuit model for putting it like that is because if you actually go to realize this, then you're kind of classical object, so we do have to have something some time order, right?
yes.
So having said that, do you think this is just as easy, like this the quantum switch is just as easy to implement as something that's time ordered, but maybe in some other way, or is it like a huge challenge, which means then from a practical point of view, it should be more advantageous to use a kind of standard circuit model, but just do a thing, implement this and
Yeah, I mean, in the spirit of the talk, I must say I have slightly changed my mind from 10 years ago to now. So at the beginning I was saying, absolutely, you can realize the quantum switch. It's even in the abstract that I cut and pasted everything. This can be realized physically, and we had really in mind this kind of interferometric optical setup. So over time, I came to be more careful on that. I would say there are at least 3 degrees of realizations. And the optical realization, it doesn't matter if you call it a realization or a simulation, it does highlight some advantages in terms of queries, number of cost of accessing. So it does, so all these advantages that we have shown kind of have a point when you implement them optically. There is a point of doing that. But I would say at least is not the highest level of realization, the strongest level of realization of the quantum switch, because it doesn't really generate the time delocalization. It already takes it for granted. It takes for granted that by interferometry, you can delocalize channel A between the first step and the second one, where for me the most exciting and more radical aspect of the quantum switch, you can take a localized channel and you can do some magic on it that delocalizes it. You can just plug it in some weird corner of space-time where this delocalization takes place. And one crazy way to do it is with the closed time-like curve. There may be kind of less crazy ways, kind of more canonical ways to get to something that looks like that. And I think we still really have a lot of work to do on the physics of the quantum switch.
I guess if you would have a loop, you would have done many other things.
Yes and no. Because that loops that appear there is kind of allowed by this kind of framework where we only do logically allowed things. So if you go to that loops framework, the question is like, it's not really what you can realize with loops, like pretty much everything. The question is which loops are allowed and which connections are what is the rule for deciding if a loop can be in the system or not? What is the analog of saying I have a circuit with time from left to right and I stick stuff from the, that's a recipe that always works, the kind of category of symmetric monoidal category with causal operations. Do these circuits, they're always allowed. If you go to closed time-like curve, it's not clear what is the rule. So that's the challenge. So,
but I wanted to clarify, and you just clarify now answering that. If you take this practical attitude and you say, well, we think switch is cool because you can do things that you otherwise you cannot do with the channel, then all implementations have this.
I'd say yes. They do show something, say you save energy, you save the cost of queries. There is always a way to say that there is something, all these advantages do mean something, but what do they mean depends on the physics. So in the optical implementation they mean something, in the gravitational implementation they mean something else, and so on. So the switch is somehow the kind of the abstract grammatical notion that contains all this physics. All right.
Okay,
So sorry
thank
for
you.
invading
Once more
the
and
time.